Hello, my name is Chen Boan, and I'm a junior student from Department of Chemistry. This is my advanced physical chemistry final report, and my topic is Eyring's reaction rate and its further application. The following representation will be based on two papers, both written by Professor Eyring and published on the Journal of Chemical Physics. The first paper that I'm interested in is the activated complex in chemical reactions, published in 1935, and the second paper suggested by Professor Xu is viscosity, plasticity, and diffusion as example of absolute reaction rates, published in 1936. In the first paper is the original derivation of the famous Eyring equation, and in the second one is shown some application of the theory. The picture shown here is a photo of Professor Eyring on his Wikipedia page. We can see that at the background is some writings regarding his famous reaction rate equation. In the introduction, I'm going to firstly talk about why I choose Professor Eyring's work. As an undergraduate student studying in organic synthesis, I initially want to find the connection between synthetic chemistry and statistical mechanics. However, I cannot find a satisfactory example. Thus, I turned to the reaction itself, and then it hit me that I can explore something related to reaction rate. Since during synthesis, the major product we will obtain is not the most thermodynamically stable compound, instead the most kinetically favored one. I believe that understanding kinetic theory helps us to understand our reaction a lot. When it comes to chemical kinetics, Professor Eyring's work may be one of the most important among all. Therefore, I want to dive into these papers. Since Arrhenius firstly introduced his reaction rate equation that treat rate constant as a function of temperature in 1889, several physicists and chemists has tried to derive more and more accurate theoretical representation of the rate constant. In 1918, William Lewis utilized hard sphere model to calculate collision frequency factor and assume it to be the A term in the Arrhenius equation. This model was in great agreement with some simple reaction, such as two hydrogen iodide forming hydrogen and iodine gas, while most of the time the predicted value is several orders of magnitude higher than the experimental one. This fact forced people to add another steric or orientation factor to correct the equation, which is far from satisfactory. In 1931, Eyring and Polanyi introduced the concept of potential surface and transition state, on which the system lies at a local minima for all degrees of freedom except one that corresponds to crossing the barrier. This is applied to also para-hydrogen conversion by Pelter and Wigner in 1932. In this paper, the author pushed this transition state theory further and used statistical mechanics to calculate a new equation for reaction rate constant. The content will be discussed mostly in canonical ensembles, and the symbols used will be chosen to stay consistent with those discussed in our course, which may or may not be the same as those in the paper. The assumption that the author made was when two molecules react, they form an activated complex which lies on the saddle point of potential surface, or the so-called transition state. The activated complex is like a normal compound, but have a unique normal mode on which the curvature is positive. This mode is what chemists now frequently draw to show the reaction pathway diagram. The author further assumed that the positive curvature is small enough that we can treat this degree of freedom as a translational one. The author firstly focused on a three-atom system. A plus BC react, to form AB plus C with a linear activated complex. The starting material has 6 translational, 2 rotational, and 1 vibrational degrees of freedom, while the activated complex has 2 translational degrees of freedom replaced by a vibrational ones. The rate constant was then calculated by multiplying the fraction of the activated complex per unit volume and the velocity on the forward direction of the reaction pathway. The former term can directly calculated via the use of partition function, with the energy difference of E0 between the activated complex and the starting material. The activated complex has one extra term of e to the power of negative E0 over kBt, and the rest are the product of translational per unit length, rotational, vibrational partition function, electronic degeneracy, and the nuclear spin terms. For the latter term, we simply average over positive momentum divided by reduced mass, and the result is the square root of kBt over 2 pi times the mass, which is of course equal to half of the 1d average velocity. A coefficient kappa is introduced to show the fraction of the activated complexes actually form the product instead of go back to the reactant, which is close to 1. If we consider the most special term here, in other words, the energy difference, the partition function for the reaction pathway mode, and the velocity, we will get a factor of kBt over Planck's constant times e to the power of negative E0 over kBt, which is also true for most of the other reactions and the core idea in this paper. The author further compared this expression with previously developed experimental results, and it is in agreement with the experimental values. Notice that the coefficient B here is in the inverse dependence of temperature. The author then considered another limit of small vibration characteristic temperature for the activated complex, which makes B now proportional to the temperature, while the experimental result should lie in between. With careful modification of each partition function term, the author provides the rate constant expression for 4-atom and unimolecular system. The general case is also given as kappa times Qa prime over Qn times kBt over h times the exponential factor, with the subscript A being the activated complex and N being normal state, in other words, the reactants. And the partition function Qa prime omits the energy difference and the reaction pathway terms, which are already included in the exponential term and kBt over h factor, respectively. Finally, the 2-atom system is calculated, and the resulting expression resembles the half-sphere collision model. The author concludes that the collision model is valid only when the vibrational modes change in activated complex can be neglected and the 2 degrees of freedom in the activated complex that replace the translational ones can be simplified to T over characteristic temperature. The steric factor in collision model can then be interpreted as the deviation of these 2 criteria. To sum up the first paper, the author provided a more general and applicable method to calculate reaction rate constant using statistical mechanics and show the origin of the famous kBt over h factor. Previously, we assumed the reaction pathway at X maximum has a negligible positive curvature and treat it as a translational degrees of freedom. If the curvature is high and tunneling need to take into account, with -4 constant f sub n and corresponding frequency I nu sub n equals to 1 over 2 pi times the square root of f sub n over reduced mass. The rate constant is then multiplied by the Wigner correction of 1 plus 1 over 24 times h nu sub n over kBt squared. A simple derivation is considering the ratio of quantum and classical limit of the vibrational partition function. In other words, the reciprocal of 2 times hyperbolic sine of h nu over 2 kBt divided by kBt over h nu. Now, if we change the frequency to a pure imaginary I nu sub n followed by Taylor expansion to the second power, we can get a correction factor. This should only be valid when the reaction pathway potential can be seen as a parabola. The author proceeded to expand the applicability of the equation beyond what we may consider a chemical reaction. First, let's look at viscosity. An ideal structure of the condensed phase was assumed to have distance lambda 1 between layers, lambda 2 parallel to the external force, lambda 3 perpendicular to the previous two, and lambda also parallel to the external force but between two equilibrium positions, which may or may not be equals to lambda 2. With shear stress F being applied to move the layer to its transition state, in other words, halfway between equilibrium, the work corresponding is force F lambda 2, lambda 3 times the distance lambda over 2. Hence, the effective energy barrier is lowered by F lambda 2, lambda 3, lambda over 2 for the forward direction, while raised by the same amount for the backward direction. The rate constant is simply multiplied by the corresponding exponential term, with plus and minus representing forward and backward respectively, which can be viewed as the velocity when multiplied by distance lambda, and the expression of delta v equals to lambda k times 2 hyperbolic sine of f lambda 2 lambda 3 lambda over 2 kBt was obtained. By definition, viscosity eta equals to f lambda 1 divided by the difference of velocity. With the assumption of the work done by shear stress is much smaller than kBt, after expanding the equation and omitted terms with second or higher power, eta is simply equals to lambda 1 kBt over lambda 2 lambda 3 lambda squared times k. If we assume that E0 is 0, all lambdas are equal, and Qn over Qa prime is the square root of 2 pi m kBt times lambda over h. Eta is the square root of 2 pi m kBt over lambda squared. By comparing this with momentum transfer theory of viscosity times velocity gradient is equals to 1/3 times concentration times mean velocity times mass times mean free path times velocity gradient, we will get L lambda squared is 3 pi over 2c. This equation can be the definition of L or lambda. A possibly better assumption is that the one more degree of freedom that Qn has than Qa prime is a vibrational one, with frequency nu I, which can be estimated from specific heat. For lambda equals to lambda 1 and molar volume V equals to Avogadro's constant times lambda 1, lambda 2, lambda 3, eta is simply N0H times e to the power of E0 over kBt divided by V times 1 minus e to the power of negative h nu I over kBt. And the resulting expression agree with the experimental result. Combined with the van der Waals equation to estimate E0, and we can see the exponential factor has an exponent of the concept of the volume occupied by the molecules over the volume occupied by the holes. Comparing the viscosity expression with Maxwell's equation for elasticity and viscosity, eta equals to epsilon tau, and assume tau equals to 1 over k, we can get epsilon equals to lambda 1 kBt over lambda 2, lambda 3, lambda squared, or approximately kBt over lambda cubed, which can be thought of as the pressure exerted by a molecule restricted to its actual volume in the liquid if it obeyed the perfect gas law. Now, if the shear stress is considerably large, as in fairly rigid structures like glasses, the first power term is not accurate enough, and a correction of a higher power term should be included. We see that this explains the observed fact that viscosity decreases with shear stress. The author also explored plasticity and obtained the dependence of time derivative of stress on the square of the stress when stress is really large, which again agreed with the experimental observation. Finally, the rate constant is taken to model diffusion. The distance between two successive layers for the diffusing molecules is lambda, and the concentration is C1 and C1 plus lambda times concentration gradient, and lambda k is viewed as the molecule velocity. We can find that the molecular flux in the negative direction is lambda squared times k times concentration gradient, which is by definition the product of diffusion coefficient and concentration gradient. Thus, the diffusion coefficient is d equals to lambda squared times k. From Stokes' equation, the drag force is 6 pi times r times eta times velocity. The well-known relationship for diffusion coefficient of large particle is obtained as d equals to kBt over 6 pi r eta. If the molecules are smaller, the author combined the expression of eta and d containing reaction rate and got d equals to lambda 1 kBt over lambda 2, lambda 3 eta. This is then applied to the diffusion of heavy water into normal water. The resulting relation between lambda 1 and the geometric mean of lambda 2 and lambda 3 was predicted previously by the author that lambda 1 is the smallest, so that in this orientation, E0 is as small as possible. By contrast, the commonly used diffusion coefficient expression gave an unreasonably underestimated radii of the water molecule. To sum up, the author introduced the transition state theory and provide a new expression for reaction rate constant, and utilize it to give viscosity, elasticity, plasticity, and diffusion coefficient formulae. Although over the past almost 19 years, people have achieved more accurate reaction rate calculation, the balance between the simplicity and the accuracy of Eyring's equation makes it the one that is taught and used among synthetic chemists, whose impact is phenomenal. It was at the first time shocking to me that the KBT over H factor can be derived with this simple assumption. While I noticed that even though the origin of this factor is not clear, in modern textbooks, people often treated the rest term as simply an exponential factor with negative Gibbs free energy over KBT as the exponent. This makes me think if it is valid when we move to NPT ensemble with the same equation, since the term QA prime over Qn should really be the anti-logarithm of entropy change over Boltzmann's constant. Now, people usually separate KBT over H factor and treat the rest as an equilibrium constant, K double dagger. While chemists usually consider a constant pressure system instead of a constant volume one, with partition functions changed into those in NPT ensemble, we can now relate Eyring's equation to delta double dagger G equals KBT times natural log of K double dagger, and the rest derivation is well known. It is noteworthy that the delta double dagger G and other thermodynamic function of the activated complex have 1 degree of freedom omitted. In conclusion, Eyring's equation provides synthetic chemists a useful tool when dealing with mechanistic study, atomizing reaction condition, and more. At the second paper, we can also see its application beyond normal chemical reaction. I believe that with careful modeling, more material properties can be calculated. With a powerful computing device nowadays, we can easily calculate the potential surface, and thus, predicting molecule properties like stability and reactivity is only a click away. Finally, the contribution of Planck and Evans on the early transition state theory is also indispensable. This is the end of my representation. Thank you.